Good morning to all of you. So let me share the PDF file now. I hope you are able to see the PDF file. So today's topic is electric field at the boundary of an interface. Okay, so if you see the syllabus, the last line in the first unit is the electric field at the boundary of an interface. So we are going to see the boundary conditions, right? So far we have learned about the electric field intensity, electric potential, okay? So many parameters we have seen. So today we will see about the boundary conditions. So why this boundary conditions has to be studied, right? So as you all know, there are different types of mediums present. If you assume the electric field can be exist or the electrons can be exist in many different types of materials such as semiconductors, metals, then insulators, semi-insulators, dielectric medium. So in all these type of materials, the electrons will be of course present, and if there is a combination of different types of these materials, right? So there will be boundaries present between these kinds of materials. So when we are applying the electric field to these materials, and if the boundary is present, that means, for example, the electrons has to travel from one medium to the other medium, then it is very much important to study these kind of conditions at the boundary between the two media. So the conditions existing at the boundary of the two media when the field passes from one medium to the other medium are called as boundary conditions. So depending upon the nature of the media, there are two situations. Mostly these two situations will come into existence. So the first one is the boundary between the conductor and the free space. Mostly the example is taken as the conductor because in the conductor materials only mostly electrons will be present, and surrounding this conductor we will be having the free space. So first we have to see about the boundary between the conductor and the free space, and then you can also assume the boundary between two dielectrics. Okay, so the example for the dielectric material is taken as air. Air is also one type of dielectric material. So similar to air, there are other dielectric materials is also available. So it will every dielectric material will have different properties. In that case, you also have to study the boundary between the two dielectrics. So what do you mean by a free space? So the free space is nothing but a dielectric. Hence, the first case is nothing but the boundary between a conductor and a dielectric, right? So if you are placing a conductor medium in a free space, that means it is having an interaction between the air medium or the surrounding medium. Even you can take about the other kind of gaseous materials. So for studying the boundary conditions, we are going to make use of this Maxwell's equations. So one of the Maxwell's equation is given here. All of you try to write down these Maxwell's equation. Later, maybe in the third unit or fourth unit, I will be exclusively dealing the Maxwell's equations. So just try to have this equation. Already you know this equation. For example, if you are having a line segment, you are going to consider this Maxwell's equation as line integral, right? So E dot dl is equal to 0. dl is the small segment present on the line segment. So the electric field passing over this small line segment will be equivalent to 0. And also you can write this particular equation as integral d dot ds. What is this capital D? Capital D is the electric displacement vector in this case, right? D dot ds. ds is the small surface which we have assumed. In that case, it will be equivalent to the total charge present on the surface. So ds is a small surface present on the entire surface area. So we have these two equations. Similarly, the field intensity, okay, so the capital E value is required to be decomposed into two components, right? So if normally in the, you might have studied about the force components, right? If force is uh, force is existing in a particular direction, that force can be resolved into two components. So normally it will be resolved in the case of velocity. You might be writing it as u cos theta and u sin theta. The same way for the electric field also, there will be two components. One component will be along the tangential direction, and the other component will be along the normal direction. So both will be perpendicular to each other. So in that case, the electric field can be represented as the addition of these two components, right? So E tangential, the tangential component is represented as E tan, and the normal component is represented as En. So the addition of these two will be collectively written as capital E. Now we'll see about the various cases of boundary conditions in detail. So first we will see about the boundary conditions between a conductor and free space. So for studying this, you might have to draw this particular picture. I'll give you some 2 minutes time. Try to draw this picture on your note. 2 minutes time. Draw the picture very carefully. So I hope you have drawn the picture, right? So here you can see that a curved surface is shown, and this dark line, okay, the curved line, the dark line is representing you the boundary, right? So below this dark curved line, we have the conducting material, that is the conductor, And above this dark line, we have the free space. You can assume the air is present over there. So it is assumed to be a free space. And four different types of scenarios are shown here. So the first one is representing you the electric displacement vector, D vector. And in the case of D vector, it is resolved into two components. One is the D tangential component and another one is the D normal component. So normal component will be a perpendicular component drawn at a point on the surface of the conductor, at the curved surface of the conductor. And the tangential component will be running along the curved surface, right? So see the right side, the electric field component is also represented depending upon the direction of the electric field of flow. So the electric field component is also resolved into two components. One is the tangential component, which is flowing along the curved surface, and the normal component will be perpendicular to the point present on the surface. So in between these two, we have two types of surfaces are shown here. We can assume one surface is like a cylindrical shape and another one surface is like a rectangular shape, right? So you can see there are 2 points shown here, 1 and 2. So 1 and 2 is the boundary of the conductor, and above the boundary we have the free space, and below the boundary we have the conducting material, right? And similarly, if you see the cylindrical material, cylindrical shape, you can see there is a boundary present. Above the boundary, we have the free space material, and below the boundary, we have a cylindrical type of conductor. So in both cases, we also have mentioned the height. Okay, height means delta H. That means it is the total height of this cylinder as well as the rectangular shaped body. And we assume the surfaces, all the surfaces present over there to be a Gaussian surface. And we are going to see the three conditions here. So consider a boundary between conductor and free space. So the conductor assumed here is assumed to be a ideal conductor. So the examples for these conductors are copper, silver. Okay. So and these kind of conducting materials will have a conductivity value, and this conductivity value is of the order of 10 to the power 6 sieves per meter. The unit for the conductivity is 10 to the power 6 sieves per meter. So I hope you have studied about what do you mean by the conductivity. And the field inside the conductor is zero, right? As we have seen in one of our earlier lectures. Normally, in the case of conductors, all the electrons will try to present only at the surface of the materials. So the flow of electrons on the surface of the material will be very high compared to the field inside. Hence, the field intensity will be zero, and absolutely the flux density inside the conductor also will become zero. And the condition number 2 is no charges can exist within a conductor, and the charges will appear on the surface in the form of surface charge density. So in that case, the surface charge density parameter also has to be included here. The charge density within the conductor also is considered to be zero. So we have three components here. One is the electric field intensity component E, and the electric displacement vector component D, and the rho V, which is the surface conductivity. Okay, so rho V means it represents the total volume within the conductor or zero. So while the rho S value is the surface charge density on the surface of the conductor. So to determine the boundary conditions, we are going to use a closed path and the Gaussian surface. So we will consider this conductor free space boundary. Now let us see the corresponding equations. As you know that, as you can see from the picture, the electric field component, this electric field component is composed of two components. That is the component tangential to the surface E tan and the normal to the surface En. So it is known that from the Maxwell's equations already we have written the integral over E dot dl is equal to 0, and the integral E dot dl carried over a closed contour is 0. That is, the work done in carrying a unit positive charge along a closed path is 0. So if it is a closed path, you have to make use of these conditions. And if it is an open type of a path, then the scenario is different. So first, let us see the rectangular case. In the picture, you have drawn a rectangular closed path A, B, C, D, E, A. See here, A, B, C, D, A. So this is a closed, so this piece is a closed path. So there are different types of surfaces present over there, right? So you can see that A to B, where this A to B is present, this is present over the conductor, that is in the free space. And from B to C, half of the portion is above the conducting medium and half of the portion is below the conducting medium. Then again from C to D, it is inside the conducting medium, and from D to A, half of the rectangle is below the surface, below the boundary, and half of the rectangle is above the boundary. So we can divide these things into 4 different components. We are going to use the equation. Consider a rectangular closed path, and we are going to trace it in the clockwise direction in this way. So it is this E dot dl will be divided into 4 parts. So basically this E dot dl can be divided, and you apply the limits starting from point and to the end point. A to B E dot dl plus B to C E dot dl plus C to D E dot dl, and then again from A to D E dot dl is equivalent to 0. Consider this one as the equation number 2. So the closed contour is placed in such a way that its two sides A to B and C to D are parallel. See the picture. A to B and C to D are looking parallel to each other, right? So they are parallel to the tangential direction to the surface, while the other two are normal to the surface, all right? So if you compare the tangential directions and the normal directions, you can see that AB and CD lines are parallel to the tangential component, and the other things B to C and D to A, they are looking parallel to the normal component. So the rectangle is an elementary rectangle with the elementary height. So the total height of the rectangle is considered to be delta H. So delta H means the difference between the highest point and the lowest point, and the elementary width, right? So did you note down the elementary width? It's nothing but the distance between A and B. Okay, delta W, and distance between C and D will be the same. So the width is taken as a delta W. So the rectangle is placed in such a way that half of it is in the conductor and the remaining half is in the free space. Plus delta H by 2 is in the conductor, and you can divide the value of this delta H also as half. The half of the thing is in the conductor and the half of the thing is in the free space. Now the portion C to D is in the conductor where E is equal to 0, hence the corresponding integral is 0, right? So the integral over C to D, that one can be taken as 0, and hence the other remaining integrals are written here. Integral A to B, B to C, then D to A will be equivalent to 0. The addition of all these three will be equivalent to 0. Now, the width of this rectangular component, that is the delta W, is very small. So E over it can be assumed constant and hence taken out of integration. So integral A to B. Okay, where is your A to B? See the picture, A to B. In that case, the delta W value is very small. So integral A to B E dot dl, bring this electric field intensity outside. It can be written as integral over A to B dl, and this integral A to B dl can be substituted with the delta W. But delta W is also tangential direction to the boundary in which the E is equivalent to E tangential. So in the place of E, you can also substitute E tangential. So integral A to B E dot dl can also be written as E tan into delta W. So we are going to replace this E with E tan. So this equation can be written as E tan into delta W. Now consider the BC direction. The BC is parallel to the normal component. So we can write the value of this capital E as En. normal component of the electric field intensity along this direction. So En can be represented as modulus of En. So over the small height delta H, En can be assumed constant and can be taken out of integration. So this is running over the distance B to C. So integral B to C E dot dl can be written as, you take this E outside, can be written as B to C dl, and E can be replaced with En into integral B to C dl. So, but out of BC, B2 is in free space. Okay, you can see here 2. Okay, see the B point. This is above the boundary and this is below the boundary. So B is in the free space area and C is in the conducting area. So this equation should be written as integral B to C dl should be divided into 2 parts. That is integral B to the point 2 dl plus from the point 2 to C dl, right? So this one is in the free space region and this one is in the conductor region. Okay. So ultimately you can write this one as delta H by 2. So this is delta H by 2 and the other one is becoming 0 here, where the value of this electric field will become 0. Hence ultimately the value of this integral B to C dl is equivalent to delta H by 2. Let us keep this as equation number 7. So this equation can again be written as integral B to C E dot dl is equal to the normal component E into delta H by 2. Write down this equation. Just a minute, I will come back. 1 minute. So the equation for the limit B to C E dot dl is equal to En into delta H by 2, right? So similarly for path D to A, that means the last part, right? So first we have seen for A to B, then B to C, then C to D, and now we are going to see for D to A. So the condition remains the same for the path B to C. So B to C is from the top region to the bottom region. This one will be from the bottom region to the top region, which will be opposite, right? So we just have to put the negative sign for this case. So integral D to A E dot dl is equal to minus En into delta H by 2. Now substitute the value of this equation number 4, 8 and 9 in equation number 3. Okay, what is equation number 3? We have 3 terms, A to B, B to C and D to A. So we have written individually for all these things. So just to substitute this one in the equation number 3, you will be getting E tan delta W plus En into delta H by 2 minus En into delta H by 2 is equal to 0. So the second term and the third term will get cancelled. So you'll be getting E tan delta W is equal to 0. So in this case, the delta W, this is the product of 2 terms, that is E tan into delta W. So either any one of the terms will be 0 in this case, right? Either E tan will be 0 or delta W will be 0. There is no chance that delta W will be 0 because definitely it will have a particular width, right? So delta W cannot be 0. So if delta W is not equal to 0, then ultimately the E tan value will be equal to 0. That means the tangential component of the electric field intensity is 0 at the boundary between the conductor and the free space. So here the key point is the electric field intensity at the boundary between conductor and free space is always in the direction perpendicular to the boundary, right? So the relation which is connecting the electric field intensity and the electric displacement vector, that is D, or the flux density D, is equal to epsilon 0 into E. You should remember this equation. We need this particular equation for deriving the Maxwell's equations. So in the case of free space, the equation is written in this way, right? D is equal to epsilon 0 into E. If you introduce the tangential component here, then d tan is equal to epsilon 0 into E tan, which is ultimately is equivalent to 0. Hence, the tangential component of electric flux density is 0 at the boundary between conductor and free space. Now, this is the tangential component. Now, let us see about the normal component. The normal component is represented as a dn, right? So in order to find the value of the normal component of D, we are going to assume a closed Gaussian surface in the form of a right circular cylinder, right? Right circular cylinder, right? Same picture. You just assume the circular cylinder. In that case also the height is taken as a delta H, and it is placed in such a way that delta H by 2 is in the conductor and the remaining delta H by 2 is in the free space. So now we are going to introduce the Gauss law here. So first we have written two equations. Let's see here. Two equations. We are going to take the second equation, which is related to the Gauss law, that is integral d dot ds is equal to q. Take that equation. So according to the Gauss law, integral over the surface. Okay, this is basically a surface integral, closed contour. The surface integral must be evaluated over three surfaces. Okay, assume the cylindrical surface. We have a top surface, we have a bottom surface, and then also the lateral surface, right? So three different surfaces are there. So this particular law can be divided into three different surfaces. One is for the top region, and another one is for the lateral region, and another one is for the bottom region. So the bottom surface is lying inside the conductor and the top surface is lying above the conductor. So the bottom surface is in the conductor where the electric displacement value D is equal to 0. Hence the bottom surface, this component. Okay, so the second term in this equation number 13 will be coming 0 in this case. Now we have the remaining two things, that is the top component and the lateral component. So integral over top d dot ds is equal to integral lateral d dot ds. Later we will be applying the limits here depending upon the situations, right? So now we have two terms, and the top surface is in the free space, and we are interested in the boundary condition. Hence, top surface can be shifted at the boundary if the delta H is directed to 0, right? So just compress this top surface and bring it just over the boundary region, and the lateral surface area, right? So it will have a particular height, and the surface area can be calculated using this formula 2 pi r h. So 2 pi r into h is replaced with delta h, right? So, and r is nothing but the radius of the cylinder. But as delta h is tending to 0, this area reduces to 0 and the corresponding integral also is becoming 0. So in that case, the lateral surface also can be taken as 0, only if we are assuming the lateral surface is just lying on the boundary, right? Otherwise, you have to use this. Equation. While component of D is present in the normal component having the magnitude dn, the top surface is very small, over which dn can be assumed constant, and it can be taken out of the integration. So take this electric displacement or the flux density outside. So dn into integral top ds, or you can also assume the small surface segment as ds, and then replace it with the delta s. So this particular equation will become dn into delta s. Now the value of substitute this particular top region in the left hand side of the Gauss law. You can write this equation as dn delta s is equivalent to q. Let us keep this as equation number 16. And at the boundary, the charge exists in the form of surface charge density, which is represented with the symbol rho s. And the unit for the surface charge density is coulomb per meter square. In the case of surface, it is meter square. And in the case of volume, it will be meter cube. So the unit is coulomb per meter square. So ultimately, you substitute the value of this rho s in the previous equation. Q value will be equivalent to rho s into delta s. So substitute the value of this q in the previous equation, that is in 16. We can write it as dn delta s is equal to rho s delta s. Okay. So we have delta s on both sides. You can neglect it. So the remaining will be dn is equivalent to rho s. Thus, we can say that the flux leaves the surface normally, and the normal component of flux density is equal to the surface charge density, that is dn is equal to epsilon 0 into En, which is equivalent to rho s. Bring this epsilon 0 to the right hand side. En will be equal to rho s divided by epsilon 0. So I hope you are trying to take the notes in this case. After the end of this hour, before 1 o'clock, I will ask you to upload what you have written in the note. I will create a link in the Google Classroom. You have to take a photograph, make it as a PDF file, and you are going to upload it in the Google Classroom. Similarly, the boundary conditions, if you are trying to arrive the boundary conditions between a conductor and the dielectric, so so far we have seen these equations. The free space is a dielectric with epsilon is equivalent to epsilon 0. So if the value of this epsilon can be related with epsilon 0 and epsilon r, epsilon 0 is the permittivity of free space, and the relative permittivity, the relation connecting these three things are given here. Then all the conditions can be written, which is shown in equation number 21, 22, and 23. That is, the electric field, the tangential electric field component is equivalent to the tangential electric displacement component is equal to 0, and then dn is equivalent to rho s, and the normal electric field component can be equated to rho s divided by epsilon 0. Replace this with epsilon 0, epsilon r. You can write this equation as rho s divided by epsilon 0, epsilon r. So these are the boundary conditions. Now I will give a problem to you. Try to write down this problem. Yesterday also I gave one problem. I hope you have solved that problem. The potential field is given as capital V equal to 100 e to the power minus 5x sine 3y cos 4z volt. Okay, here capital V refers to volt because it is a potential, electric potential. So the unit is volt. The potential equation is 100 e power minus 5x sine 3y cos 4z. So this is XYZ component, which is a Cartesian component, Cartesian coordinate component. Let the point P, the coordinates of the point P is given 0.1, pi by 12, pi by 24. They are located at a conductor-free space boundary. At the point P, find the magnitude of, at the point P, find the magnitudes of. There are 5 different problems are given, right? A, B, C, D, E, F, G, sorry, 7. So based on the boundary conditions, you can take whatever equations are required and try to find out the magnitudes of the electric potential V, and the electric field intensity E, and ET refers to the tangential electric field component, and EN refers to the normal component, and the capital D refers to the electric displacement vector or the flux density, and dN represents the normal component of flux density, and the rho s represents the surface charge density. So try to solve these two problems, and also before 1 o'clock, try to solve these problems and try to upload the solution of these problems also. So today's topic as well as the solutions of these two problems. Yesterday I gave one problem and today I am giving another one problem. Try to find the solutions, and I will create a Google Classroom link